All right, so let's get started. Now, today's session, once again, welcome everybody. We are going to be covering on chemical bonding. Okay, so for this session, covering on chemical bonding. Now, I'm going to start the session by doing some recap. Okay, if you have an empty space on the notes or you have a piece of paper, let's do this recap together. Now, can anybody tell me, right, if I have a noble gas, can someone name me what are examples of noble gas? Any idea? Just give me some noble gas inside the chat. Okay, this one, okay, thank you. Yeah, I see your answer. Okay, Talina, thank you. Argon, Jing'en, thank you. Argon, okay, very good. Okay, so we have helium. Okay, thank you, YJ. We have a lot of answer, right? So now, how do we find out? For some of you who are really not sure where to find, okay, let's go to your periodic table. Let's study this together. Now, this is how your periodic table look like. Now, group 18 element. Okay, this group, I'm going to highlight for you. Now, group 18 elements, they are known as noble gas. Okay, these are known as noble gas. Now, whenever we come across noble gas, what is the most important thing? Okay, let's go back to the notes. Now, what is the most important thing is we need to study what is their electronic configuration. Okay, remember in atomic structure, we study about electronic configuration. So we are going to look at the stability, the stable electronic configuration. All right. Now, okay, I still have some more students joining us. Okay, very nice. So those who have just joined us, thank you very much for coming today. If you have the notes, please download, and then after that, you can write along as well. Okay? All right. Now, back to noble gas. Now, noble gas always have this thing called the stable electronic configuration. Now, what does that mean? I'm going to illustrate to you. What are the stable noble gases, as well as example on how you can tell whether it's stable or not stable. Now, let's use example given by YJ. YJ says helium. Very good. Okay, now helium, how do we draw a dot and cross diagram? Let's go to the periodic table. Helium is this one over here. Now, I know that helium, the top number, always the top number refer to proton number. Okay, the proton number. Now, for proton number, helium have 2 protons. Okay, got 2 protons. Now, that means that whenever we talk about an atom, okay, an atom of helium, the number of protons must be equal to the number of electrons. And that means helium got 2 electrons. Everybody agree with me so far. All helium atom got 2 electrons. So I'm going to display it out for you over here. Now, 1 electron, 2 electrons. Now, remember, what is the principle for electronic configuration? The first electron shell, the most inside one. Okay, anyone type to me in the chat. How many electron maximum can it hold? How many electron? First electron shell. Okay, Victoria, thank you. Arisa, thank you. 2, yes, very good. So we have 2 electrons, right? So 2 is the maximum already. Now, let's use another idea. Okay, let's use another next one. We use neon. Now, we go back to periodic table. Neon is this one over here. So neon, okay, I erase, if not you cannot see. Neon got 10, right? So 10 electron. Now, neon got 10 electron. That means, okay, so original will be like 8. Now, these are 2 electron in the innermost shell. And then the next shell, okay, the next shell over here, they have 8 electron. So 8 electron is going to look like this. Okay, everybody agree with me this. Okay, now I want to guide your understanding. I don't want you to memorize. Okay, chemistry, we don't memorize one. We need to understand. When you understand, very simple already. Okay, so now helium got 2 electrons. Okay, this is 2 electrons. Now, this electron shell is full, right? Because the number 1 shell can only hold 2 electrons. This is full. Very good. Now, what about neon? Neon here got 2 electrons. Now, the valence electron shell, the second shell over here, can anybody tell me what is the maximum capacity of this second electron shell? How many electrons can it hold? Talina, thank you very much. Akila, 8. Okay, very good. Arisa, 8. Very nice. So that means that for neon itself, we also full, right? This one is full. No more space for any other electron. We already got 8 electrons already. Okay, so with 8 electrons in mind, we are saying that this is full. Now, whenever we have a full electron valence shell, okay, valence electron shell. Now, once again, for those of us who are not familiar with the term, valence simply means outermost. Okay, outermost electron shell. Okay, valence simply means outermost electron shell. Now, this is full. This one also full. What does that mean? We always say that noble gas, for example, helium and neon, when they have a full valence shell, we call it stable. Okay, we call it stable. Now, you may be wondering, Mr. Cole, why you teach me all this? Why you teach me all this? A bit don't link to chemical bonding. Okay, I'm going to show you. Now, whenever we say noble gas, okay, whenever we say noble gas, we need to understand that this structure of a full electronic configuration is whatever every single atom wants to achieve. Okay, so understand together with me, every element, okay, every atom, okay, wants to achieve, okay, what we call a stable electronic configuration. You understand this with me? So for example, no matter oxygen, lithium, sodium, etc., every single atom of these elements, they want to achieve a stable configuration. That means they want to have full valence electron shell. Now, this will help us guide us in what we call chemical bonding. Okay, let's look at this carefully. Now let's go to the notes. Now, I'm going to give you an example, okay? For those of you who need to copy down, or maybe you want to just write down this, okay, give you 3 seconds, okay? All right, time's up. Next. Okay, moving on over here. Now, this one you can find in the notes. This is the first page of the notes. Now, I'm going to give you an example. Okay, I'm going to give you an example. I have sodium over here. Now, can anybody tell me, sodium, what is the electronic configuration? Okay, I show you the periodic table. Sodium is over here on the left-hand side. Can you tell me what is the electronic configuration? Type to me inside the chat. Okay, thank you, Talina. Very fast. Anybody agree or disagree with Talina? YJ, thank you very much. Akila, thank you. Okay, so yes, you are absolutely correct. Sodium has an electronic configuration of 2,8, number 1. Now, every single atom, remember, I just now tell you a story already. Just tell you a story, noble gas, right? Every single atom, this sodium atom, they want to be like a noble gas. Okay, they want to be like a noble gas. Now, there are 2 ways for this sodium atom to become a noble gas, or rather to have the same electronic configuration as a noble gas. Now, I'm going to show you 2 ways. The first way, okay, method A, agree with me, 281. Remember, my valence electron shell can hold how many? Okay, valence electron. Okay, valence shell can hold up to maximum 8 electrons. Now, that means for scenario A, method A, what I can do, I can lose 1 electron. Agree with me, this electron I throw away. If I throw away, then okay, what? This is my valence shell, my outermost shell already. This shell don't have already. Then that means, yes, correct. My valence shell is full, maximum 8. Can? Okay, so let's understand this first. So if I lose 1 electron, what happened? Sodium electronic configuration going to become 2,8. Now you may be asking, okay, I throw away 1 electron, then what happened? Right? What happened? Now, sodium got 11 proton, original. It have 11 electron, original, because 2 plus 8 plus 1, 11, right? Now, once I throw away 1 electron, now it become left 10 electron. Now, left 10 electron, Now, left 10 electron, that means this sodium gonna have positive charge, right? Because now I got 1 more proton and electron, Now I got 10 electron. Now, this is scenario number A. Let's go to scenario B. Now, scenario B is a little bit more special. Now, instead of I don't want to throw away this one, I want to keep this one. I want to find another 7 more, right? I gain 7 electron. Okay, gain 7 electron. That means I'm going to have a structure of 2, 8, 8. Wow, this number 1 become 8. I need to gain 7 electrons. Now, can anybody tell me, type inside the chat, A or B, which one is the one sodium is going to do? A or B? Are they going to throw away 1 electron, or are they going to find 7 electrons from somewhere? Okay, everybody say A, very good. Anybody say B? Must be different, confident and different. Okay, thank you, Charlene. Thank you, Sarah. I see all your answers. Thank you very much. Keep the answers coming. Now, yes, you are right. A is the preferred option. B cannot. Why? Explain to you. So, for example, I am a sodium atom. Now, sodium atom means I got 281. For me to go and find 7 electron, I need to go and beg 7 other people for it. Hello, sir, you got extra electron? Give me. Or I need to find 7. However, if I decide to throw away my 1 electron, sir, I got 1 extra electron, I give to you. Then I'm settled already. So it's definitely easier for me to throw away 1 electron to form what we call this sodium ion. Okay, so you see, sodium is going to lose 1 electron to form a positive ion. Okay, get me so far? All right, now let's look at the definition. Okay, any question? If not, let's look at the definition. Now, in elements and compounds, what happens is that each particle, they are held together by this thing known as chemical bonds. Okay, important, chemical bonds. Now, what does this mean? I give you an atom, or rather, I give you a molecule of water, H2O. I draw the molecule out for you. Okay, looks something like this. I got the oxygen in the center. Now, you may be wondering, now I got hydrogen. Okay, yes, I got H2. I got oxygen also. Now, how are all these going to connect together? If not, I got so many H, so many OH. What happened, right? So what happens is that all of these, it turns out that every single particle in this world, okay, whether or not is it molecules, they will always have chemical bonds. Okay, this one over here, the one that I just drawn, okay, this blue color one over here. These are known as chemical bonds. So they are like, for example, like a bridge between each of the 2 buildings. Okay, so that I can connect the building together. I don't want the building to go not connected. I want the building to connect together to tell me that, okay, this is one compound. This is one compound. Remember, your HDB got many, many blocks. Every block, if let's say they got a building together, or rather they got a bridge together, they are now one compound, right? Now, a chemical bond is defined as a force that is holding particles together. Now, what are the most important part of this page that we see over here is there are 3 main types of chemical bonding. Now, I'm going to explain each and every one type, okay, and then after that, we'll go in to look at it in detail. Now, first off, let's look at the first one. Number 1 is called ionic bonding. Okay, ionic bonding. Now, ionic bonding, as the name suggests, it must always involve ions, right? Because it said ionic bonding must always have ions. Now, what are ions? Remember, ion and atom got different. Just now we say this one over here. This is a sodium atom. While this one over here is a sodium ion, right? What is the difference? The atom, they got no charge. Whilst the ion, they have a positive or a negative charge. Okay, remember, ions are charged particles. Now, we are also going to learn that for ionic bonding, this takes place when? This takes place when metal undergo chemical bonding with non-metal. Okay, write this down first. Find a space to write this down. Don't worry, now you question, what does metal bond with non-metal mean? Later we will go into it, okay? Now, the number 1 type is called ionic bonding. Move to number 2. Number 2 is called covalent bonding. Now, the word covalent stands for what? Co simply means sharing. Okay, co means sharing. Valent means what? Just now we said valence electron means it's the outermost electron. Okay, outermost electron. So what happens is two atoms, they will come together, they will share their outermost electron. You see the name? Covalent means I share my valence electron. Okay, got me so far? Okay, all right. Now, if you have any question, once again, please don't be shy. Just ask in the chat, okay? If you're shy, never mind, you just direct message to me. Okay, no need to share with everybody. But I recommend if let's say I ask for questions, maybe you can share with everybody. Then we learn together. Okay. Now, covalent bonding happens when non-metal, a non-metal bond with another non-metal. Okay, this is when covalent bond happen. Non-metal bond with non-metal. Now, last but not least, we look at metallic bonding. Okay, let's look at metallic bonding. Now, as the name suggests, metallic bonding simply means bonding within metals. Bonding within metals. Now, that means it's a metal bond with metal. Okay, when we look at these three types of bonding, every type of bonding will have what? Will have physical property, will have a structure, will have a bonding explanation. So we are going to go into each of them later. Okay. Now, what is most important for you to know is elements and compound that are formed by these different type of bonding. For example, something that is formed by ionic bonding, covalent bonding, and metallic bonding, they are very different from each other. Okay, they are very different from each other because you understand bonding is what? Bonding is the connection, right? The bridge. Some of the bridge is okay, like that straight bridge. Some of the bridge, okay, is like that crooked bridge. Some of the bridge is maybe some is high bridge, some is low bridge. Different ma. Okay, some is glass bridge, some is metal bridge. Different. Okay, and that's why different type of chemical bonding have different structure. So I build a bridge with a different structure. Okay, now different structure of substances give rise to different physical property. Now, what are physical property? Very simple. For example, melting point, boiling point, the solubility in water, whether or not can dissolve. I put inside water, will it dissolve? Okay. All right. Now, this page, and so far, any question? No question, can give me thumbs up. Anyone have any questions? Okay, thank you, C, for your thumbs up. Thank you, Charlene. Thank you, Hewon. Thank you, Melody. Thank you, Sanjit. Okay, I see all your thumbs up. Thank you so much, YJ, as well. Okay, now I'm going to move on to the next page. Okay, I'm going to move on to the next page. If you have any question about this, later you can ask me also. No worry. Now, let's go into each of the bonding specific on a specific level. Now, first, we look at ionic bonding. Okay, ionic bonding. Now, just now I tell you what? Just now I tell you sodium, right? Sodium is 2,8,1. Agree with me? This one just now we already discussed. So for sodium to become a stable noble gas configuration, to have the stable noble gas configuration, what it's going to do is going to throw away, right? It's going to throw away is one electron. And what it's going to become is going to become the sodium ion, which is positive 2,8. Okay, so this is the sodium ion. Now I'm going to use another example. Okay, I'm going to use another example. Let's come to our periodic table. Now, our periodic table, let's choose this one, the one in pink, chlorine. Okay, chlorine, look at this number, 17. Remember 17, 17 electron, chlorine. Now, we go back to our notes. Now, chlorine have an electronic configuration, got 17 electron. So the electronic configuration is 2, 8, 7. 2 plus 8 plus 7 is 17, right? Now, can anybody tell me, chlorine, if it's going to obtain the noble gas configuration, is it going to gain or lose electron? Can type to me in the chat. Is it going to gain or lose electron? Okay, thank you. Thank you, YJ. I see your answer. Okay, thank you, Talina. I see your answer. Thank you, Arisa. Okay, very good. So most of y'all say gain. Okay, very good. Wonderful. Now, you are right. 7 to give me 8. Very simple. I just need to gain 1 electron. Now, so hence my structure is going to look like this. 2, 8, 8. Now, many students when they write this sign over here, is it going to be positive or negative? Now, many students tell me it's going to be positive, and Mr. Koh, going to be positive. Why? Because I gain electron, I plus electron. Remember, electron is negative. Electron is negative, okay? Hence, if I gain a negative particle, of course, chlorine is going to become chloride ion, negative charge, -1. Okay, remember, so you must compare carefully. Now, you need to remember this one, you are dealing with electron. So if I gain electron, I'm gaining a negative charge. Now, with this understanding, now why I choose chlorine, why I choose sodium? Very simple. Very simple, right? What is the reason? You see over here, sodium is 2, 8, 1. I want to throw away my 1 electron. I need somebody who can take my 1 electron. I cannot just throw to somebody. I cannot just throw outside randomly. I need somebody to be able to take, okay, to take this electron. So what I'm going to do now is this sodium, they have just found a partner, which is chlorine. So chlorine say, hey, I want 1 electron. Sodium say, hey, I got 1 spare electron. I give to you. And that is exactly the reason why this is known as the transfer of electron. Okay, now you must always remember, electron always transfer from metal to non-metal. This is very, very important. Okay, electron transfer is always from metal, sodium throw away, to chlorine. Chlorine is a non-metal. Okay, for those of you who don't know yet, my periodic table, left-hand side is metal. Right-hand side is non-metal. Okay, so you must be able to know this. Now, back to the notes. Let's just recap what we have just gone through. Metal, they lose electron and they form positive ions. Okay, get me so far? They form positive ion. Now, this positive ion, they have a special name for it. Start with C1. Can anybody tell me? Can anybody tell me? Okay, thank you, YJ. You have the correct answer. Anybody else? Okay, thank you, C. Cation. Anybody else? Want to try? Okay, Celeste, Talina, thank you. Sarah, Valerie, Victoria. Now, I know that sometimes it may be difficult to think on the spot, but of course, remember in exam time, sometimes we need to be fast. Okay, not to worry. Okay, as we go along the lesson, we are going to progress in terms of our confidence in answering. If we don't know, it's okay, no worries, because everybody here is to learn, right? Everybody here is to learn. Now, answer is correct. Cation. Okay, somebody say cation, not cation, cation. Okay. Now, non-metal on the other hand, they gain electron. They form negative ion. Anybody tell me, negative ion is called what? Negative ion. Okay, Talina, very fast. Okay, anion. Okay, very good. Answer is anion. Now, how to remember? Somebody asked me. It's very difficult to remember. Actually, quite easy one. Whenever, okay, I know everybody use TikTok here. Now you open a TikTok, you see cat. Wow, you see cat, very happy, right? You see cat, wow, so nice, so cute. You become very positive. Then, if let's say you scroll across the TikTok, later you see National Geographic one. Now you see a lot of ants. You see a lot of ants. Wow, so disgusting, right? Negative. Okay, so you see, cat, positive ion, anion is a negative ion. Okay, just remember this. So, metal from cation. Cation are positive. Non-metal, they form negative ion, anion. Okay, now they lose electron. Metal lose electron to where? Metal give the electron to non-metal. Okay, transfer of electron, remember, is always from metal to non-metal. Now, with this understanding, then we can start to explore what does ionic bonding mean. Now, look at this carefully. I'm going to highlight this. on the top. I got Na plus and Cl minus. Now remember, magnet, North Pole and South Pole, they will always attract, right? North Pole and South Pole, opposite pole will attract. Same for this, positive and negative. What happened? They are going to attract each other, right? They will attract each other. Opposite charge will attract. Okay, positive will meet with negative. If I have positive and positive, they will repel, okay? Positive and negative, they will attract. Now, that means this orange color line that I draw over here, now this line is what we call the ionic bond. Okay, get me so far? Now, this line over here is called the ionic bond. Now, the ionic bond is otherwise defined as the strong electrostatic force of attraction. Okay, strong electrostatic force of attraction. Now, it is between oppositely charged ion. That means it is definitely going to be one positive ion and one negative ion. Okay, get me so far? Now, this bonding, they hold positive and negative ions together to give ionic compound. Okay, so when there is an attraction between a positive and a negative, they will form a compound. It's called ionic compound. Now, the electrostatic force of attraction, now this term is very, very important, very, very crucial for you to remember. Why? Because electrostatic force of attraction, now electro and static simply represent positive and negative. It's always talk about charge, right? Charge is like electricity, right? Okay, so because they are statically attracted to each other, we call it the strong electrostatic force of attraction. Okay? All right. Any questions so far? If no question, can give me thumbs up. So I know all of you are good. Okay, thank you, Melody. I see your thumbs up. Thank you, Jing En. All right. Okay, let's move on. Now, I'm going to use this example. Just now I used the example of what? NaCl, right? I'm going to use this example now of magnesium chloride to show you the formation of ionic bond. Okay, now first off, magnesium atom. Let's look at the magnesium atom over here. Now, the magnesium atom have two valence electron. Okay, got two valence electron over here. Now, what is going to happen is that since magnesium, I'm a metal, right? Metal, they always lose electron. They form what? Lose electron, they form positive. Positive, we call what? Positive. When I see cat, I'm very happy. So cat ion. Okay, now, this magnesium atom is going to throw the electron to a chlorine atom. Now, remember, chlorine got 7 electrons. So you see over here, my two blue color over here. Now, this number 1 blue color will come here to fill up this gap. This number 2 blue color will come over here to fill up this gap. And that is the reason why the magnesium is going to become positive, 2 positive because they throw away 2 electrons. And chlorine is going to, every single one of the chlorine going to have 1 negative charge because they just gain 1 electron. Okay, so when we draw in the dot and cross diagram, you can represent it like that. Okay, you can represent it like that. Or you can just put a 2 in front of the Cl. Then you just cancel away this one. No need to draw this one. Okay, just write 2 over here. Okay, it just represents 1 of these and 2 of the Cl. Can? Okay. Now, then they're going to ask you, what is the chemical formula for magnesium chloride? So MgCl. Now, MgCl or not? Or is it MgCl2? Okay, how to know what is the chemical formula? Very simple. Now, Mg is going to donate 2 electrons away. They're going to become 2 plus, right? Now, chlorine is going to gain 1 electron. So become minus. Now, how to find out what is the chemical formula? Very simple. I crisscross. So I'm going to have MgCl2. So I follow this number. This one is 1. This is 2. So the 2 come here. The 1 come here. Okay, this 1 minus. So hence, I get MgCl2. Okay, so this is a very fast way for you to understand how to find the chemical formula of something. Okay, based on the charge of each ion. Okay, okay, moving on. Now, once we have learned about ionic bonding, we need to learn about what kind of structure it formed, right? So we learned about the bridge already. Now, this is what goes on in the bridge. Now, we are going to look from outside. Outside, right? When we look at the 2 HDB block, they are connected by this bridge. How does the bridge look like? This is what we call the ionic structure. Okay, moving on. Now, ionic structure, this one also inside your notes, not to worry. Okay, now what I'm going to do now is that I'm going to explain to you what ionic structure is, okay, and how does ionic structure look like. All right, am I back? I think I am back. Fantastic. Okay, now back over here. Just now I say, okay, sodium and chlorine. I repeat again. So just now we talked about oppositely charged ion. Now I got one sodium, I got one chlorine. They are going to attract each other. One sodium, one chlorine. However, actually, in the real scale, is it actually just one sodium and one chlorine? Actually got many, few thousand million of these ions. And that is the reason why whenever I have these, it will give me this sort of a square shape. I'm going to draw this for you, see whether it makes sense for you. Like that. Okay, so it looks something like this. Why? Because you see, the positive attract the negative attract the positive, and the positive attract the negative. Then this one attract this one, vice versa. Basically, all of this sides, all of the four sides, they will attract each other. Okay, now this form the basis of what we call the structure, the bridge structure. Now, look at this picture over here, the one at the bottom. You can see clearly that there's blue, there's yellow. Okay, so the blue and the yellow are alternating. That means that you have one sodium, you got one chloride. You got one sodium, you got one chloride, etc. And that is exactly the reason why the ionic structure look like this, because they are in this electrostatic attraction. The strong electrostatic attraction means that they are going to be arranged in an orderly and closely packed manner. Now, question in exam. Describe to me what does an ionic structure look like. Then you must tell me yes. Oppositely charged ions are held together by strong electrostatic force of attraction. Now, keyword over here, strong electrostatic attraction. Go on and tell me. They are in an orderly and closely packed manner. They form this giant ionic structure. Some school, they teach it as giant ionic lattice, right? Which is the same thing. Now, positive ions and negative ions are arranged on a repetitive manner, okay? So I have one positive, one negative, one positive, one negative. Can I? Okay, I hope that this is not any issue for you. Can I go a little bit faster? Okay, let's go a little bit faster. Now, for ionic structure, let's look at physical properties. Now, just now the structure this structure over here, the one that you see over here. Let's look at the structure, the properties. Now, this bridge, this structure have a property that is as such. They are hard but brittle. Okay, so you see, they have this cube, look like cube like that, right? So they got 1, 2, 3, 4, all the atom at the end. What it's going to become is because of the strong electrostatic force of attraction, positive and negative, they attract very strongly. They have strong ionic bonds. But when this bridge is hit, very easily broken because it's very brittle. Now, you need to know this. They are crystalline solid with flat side and regular shape. Because of the fact that all the ions are in one straight line, they are in like a square shape, they have flat side. Now, what is most important for giant ionic structure is this. They have high melting boiling points. Okay? Because of the fact that you know that the positive ion and the negative ion, they have this super strong force of attraction. Sorry, strong also spelled wrong. Okay, O-N-G. Okay, strong force of attraction. Now, it requires a lot of energy. I need to supply a lot of energy to be able to break this. Right? For me to break this bridge, I need very strong. Okay, a lot of energy. Strong men to be able to, strong men and women to be able to break the bridge. Okay, so hence I need a lot of energy. And this form of energy always come, or most of the time it comes in terms of heat. Okay, now, if it comes in heat means what? I need a lot of heat energy. That means the temperature must go very high. That means they got high melting and boiling points. Okay, so it flows in a sequential manner. Yeah, I show you again. Number one, I understand positive and negative. What happened? They attract very strongly, very strong force of attraction. Number two, since they got very strong force of attraction, I need strong men and women to be able to break this bridge. Okay, and in this case, whenever we are in the lab, we use what? We use heat energy. We use, flame. Now, flame to heat this. And what does that mean? That means that I need a very large amount of energy to be able to melt or boil this. Okay, melt or boil this. Okay, now next one, low volatility, no smell. Okay, this one no need to say much. It's not very important. Most important is the one in purple. Okay, all right. Now next, ionic compound. They are soluble in water. Now this is something that you need to know. Very important. Soluble in water means can dissolve in water, but they are insoluble in organic solvent. Okay, that means I dissolve in water, it's going to become ion. So for example, now I have this structure, right? I got positive, I got negative, I got positive, I got negative. Now I take this structure, okay, so this one is a beaker of water. Okay, imagine this one is all water. Now I'm going to take this structure, throw inside water. Now what's going to happen is that all of these ion, okay, or rather all of these ion, they are not going to have any so-called bonds, but they are going to just float around freely in solution. Okay, they dissolve, the bond dissolve, and these, they are free to float about in the solution. Okay, now because why? This one, an explanation not very necessary for you to know. Okay, not very necessary for you to know. They attract water molecules, disrupt all these not very necessary for you. You just need to know because they are positive and negative. When they throw inside water, they can break up. Okay. Now next, electrical conductivity. Now in the solid state means inside just now this configuration. Inside just now this configuration, they cannot conduct electricity. Why? Because every positive and negative, they are fixed at the same spot. They cannot bring the charge anywhere, right? I give you electricity, it cannot go anywhere. But what happens is when I throw it back into the water, remember just now it's inside the water already. Now, I give this ion a charge. Now, this ion can move somewhere, ma. I give this ion a charge, it can move somewhere. So it can help me to conduct electricity. Okay, so it can conduct electricity when in molten or aqueous state. Now, I got some question. Okay, question. The electrostatic force of attraction is the ionic bond. Yes, that is correct. The strong electrostatic force of attraction forms the ionic bond. Okay, now some students who are private candidates, okay, what happens is the syllabus have changed. I'm going to discuss that with you later on. Allow me to discuss that with you later on. Let me just proceed with the lesson first. Later we will talk about this. All right, now moving on. Covalent bonding. So ionic bonding, we finished already. The structure that we need to learn, most important keyword is giant ionic structure. And what does the ionic bond stand for? They have a strong electrostatic force of attraction. Remember this? Strong electrostatic force of attraction. That is the most important. Okay, now I move on to covalent bonding already. I realize I'm slightly behind time. Okay, I'm going to go a little bit faster. Okay, if you are not comfortable with the pace, want me to slow down a little bit, please let me know also. Now, covalent bonding. Remember the word covalent stand for what? Co stand for sharing. Valence stand for valence electron. Okay. They are sharing pair of electron. Now, covalent bonding, they are formed between atoms of non-metals. So for example, that is the reason why we have oxygen molecule, O2, because oxygen is a non-metal, right? So they will form bonds between each other. Now, it can be found in element and compound. So for example, as mentioned just now, we have O2, we have H2, and we got nitrogen also. Now, between elements of different compound, for example, we have CH4 methane and H2O water. Okay, so it does not necessarily need to be the same element. It can be different element, but as long as they are all non-metal, okay, they are covalent. Now, sharing of electron, how does it work? They are going to share electron in order for the atom to obtain a stable electronic configuration of a noble gas. So remember, every atom, what they want is exactly the same. They want a stable electronic configuration. That's all, finish, end of story. I just want to get this structure. Okay, I'm happy already. I want all my valence shell electron slot to be able to be filled up. Okay, now let's look at this carefully. I'm going to use oxygen as an example. Now, oxygen molecule. Now, I know that oxygen in a periodic table is over here, right? Over here, I highlight in red for you. 8 electron. Now that means that the structure is 2, 6. Electronic configuration is 2, 6. Now that means they got 6 valence electron. It requires 2 more electrons to obtain a stable octet configuration. That means what? That means I'm going to get 2 electrons from sharing. I share with somebody else. Okay, let's see over here clearly inside this picture. Now look at this. I'm going to color code the electron for you. Now look at all the green electron. It belongs to the oxygen on the left. Now look at all these purple electron. Now all these purple electron belong to the oxygen on the right. Now what happens is that they are going to come close together. These 2 oxygen on the left and the right, they're going to come close together. And there's this sharing zone. What happened? Basically, I got a table, right? I'm going to put my electron on the table and it's going to be counted as your electron and my electron also. Okay, we are just sharing electron. So sometimes I can take, sometimes you can take. But most importantly, we all have the electron. So that means how do I count? If I count from the left, oxygen number 1. Oxygen number 1, I got 1 electron, 2 electron, 3 electron, 4 electron, 5, 6, 7, 8, 9, 10. 10 electron, that means 2, 8. So means I got 8 valence electron. I'm happy already, right? Now I count for oxygen on the right hand side, oxygen number 2. Now, yes, I got 2 valence, I got 2 innermost electron in the first shell. For valence, I got 1, 2, 3, 4. I count the green one also, 5, 6, 7, and 8. Right? I got 8 electrons. That means both of us are oxygen number 1 and oxygen number 2. We are all happy because why? We got both 8 electrons on the valence shell. That means we are all going to so-called have the stable electronic configuration. Okay? All right. Now, this is in element, which means oxygen only. Next one, we are going to look at in compound. For example, methane molecule. Now, methane have a structure of CH4. Methane have a structure of CH4. And what is going to happen is that because carbon have a structure of 2 and 4, 2 and 4 like this, and hydrogen only have 1 electron. Remember, hydrogen only got 1 electron. Now, how does it work? This hydrogen gonna come here, right? Remember, okay, wait, let me, before that, look at the carbon. Now, the carbon in the outermost shell, remember, outermost shell can hold 8 electrons, right? So I got 1 spare lot over here, 1 spare slot over here, 1 spare slot over here, 1 spare slot over here. What is going to happen is because hydrogen is only got 1 electron. But for me to become stable, I need 2 electrons, right? Remember, 2 electrons, right? In my first shell, I need 2 electrons. That means this hydrogen gonna come here. And then another hydrogen is gonna come here. Another hydrogen is gonna come here. And another hydrogen is going to come here. Understand me so far? So every single slot over here, they got 1 hydrogen, right? Because at the end of the day, now my hydrogen is happy because now each hydrogen, you see, they got 2 electrons. They got 2 electrons. Means everybody happy already, right? Now carbon, they got 2 electrons in the center. Okay, very good. Now my valence shell, my purple color shell, highlight the purple color shell for you. This is my purple color shell. Now, count carefully. I got 1 electron, 1 from hydrogen, 2 electron, 2 from hydrogen, 3 electron, 3 from hydrogen, and 4 electron, and number 4 from hydrogen. That means total I got 8 electron. And that means I'm happy already, right? Carbon is happy. Why? Because they got stable 8 electrons on the outermost shell already. Okay, so there is a simple explanation on how does methane actually works. So they actually form 4 covalent bonds. All right, so they form 4 covalent bonds with the hydrogen. So I got 1 bond, which is like that, C and H, they form 1 bond. Number 2, C and H form 1 bond. Number 3, C and H form 1 bond. And number 4, C and H form another bond. So they got 4 covalent bonds. Okay. All right, so now there are other examples like water, ammonia, carbon dioxide. I'm not going to go into it. Okay, you can read the exercise over here. Okay, now covalent structure. Once we already understand what goes on inside the bridge, we learn how does the bridge look like. Okay, so now covalent structure got 2 types. Okay, important 2 types. Now the first type is called the SMS. Not the handphone, not the handphone I text to your friend. Now, SMN stands for simple molecular structure. Now, what does that mean? Simple molecular structure. You say simple, is it really simple? Yes, I tell you, it's very simple one. Now, oxygen. I know oxygen look like that, right? So I got two, I got electron. Yeah, oxygen look like that. O2 ma. O2, right? So remember, O2, they got two pair of electron they are sharing. Now, like that only, this is one oxygen molecule. Very simple, right? Yeah, finish. Now I got water, for example. I got H2O. It is H2O. Yeah, look like that. Simple also, ma. Very simple, right? That's why it's called simple molecular structure. Now, what is simple molecular structure? They are found in element and compound consisting of small molecule. So what does that mean? That means, for example, I got a molecule of water, H2O. I got another molecule of water, got H2O. And I got one more molecule of water. Okay, I never draw the electron, but I just show you how does the water molecule look like. Now, this is known as simple molecular structure. Why? Okay, look carefully. Between the hydrogen and oxygen, do you agree with me just now? We learned about the sharing of electron. They are covalent, they share electron, right? They share electron. Now, between each of these water molecule, because the water need to stay together, there actually exists this force. Okay, this force over here between each of the water molecules. Now, this is known as weak intermolecular force. That is the reason why water molecules like to stick together, because they got weak intermolecular force, right? But I can still pour water because the weak intermolecular force very easily broken. Weak, ma. Remember, whenever we say weak, that means I need low energy. Very little heat I can break already. Okay, very little force I can break it already. Now, this is for simple molecular structure. Next, giant covalent structure. This one is very giant, very difficult to understand. I'm going to go to the next page, then I tell you. Okay, now giant network of atoms, they are held together by strong covalent bonds through the whole structure. Okay, this one, I'm going to leave it later. Let's look at this structure first. Now, two types over here. Clearly, this photo is over here for me to drive back the point. Simple structure actually look very simple one. You see, this is known as a simple. This is a SMS, simple molecular structure. Okay, now the one on the one on the right hand side, on the other hand, this is called giant molecular. Okay, simple molecular. I got very, very small, simple molecules. Giant molecular, I got very, very big, gigantic molecules. The name is self-explanatory. Okay, now SMS and GMS. Okay, SMS, for example, water, oxygen, carbon dioxide, they are all simple. Now, giant molecular structure, they have three types that you need to learn. The first one is known as diamond. The second one is known as graphite. And the last one you learn is called silicon dioxide. Now, diamond and graphite, they are all made of carbon atom. Now, scientists actually found out that carbon atom, they really like to do this. They go for diamond structure, do like this, or they go for graphite structure. So see which one they prefer, right? So some of the carbon atom, it turns out they become diamond, right? Diamond have this very nice structure, look like building blocks, right? So you can see pyramid like that. In the center, I got one. I connect to one at the top, connect to 1, 2, 3 at the side. Look at this. I count again for you. I got one over here, one at the top, 1, 2, 3 at the side. This carbon atom. Now, all these one are all referred to carbon atom. Now, graphite on the other hand, is a little bit more fun. Why I say so? Look at this, this carbon. I got 1, 2, 3. Now I got 1, 2, 3. Remember, I only got 3 bonds. This one over here on diamond side, I got 1, 2, 3, 4. Right? Now, I'm going to tell you why I say this very carefully later. Diamond got 4 bonds. Remember this. Okay, remember this. Graphite, each carbon atom, they got 3 bonds. This will have implication later. Now, graphite look like this. These are hexagonal rings, okay? Hexagonal rings. So how we describe this? This is called hexagonal rings. Maybe you want to write this down. Okay, hexagonal rings is used to describe each one of the ring. Now, if you are looking at the whole structure from top to down, it's called layers of hexagonal rings. I got 1 layer, 2 layer, 3 layer, 4 layer, like multi-story, you know. Now, diamond on the other hand, this pyramid kind of arrangement, they have a special name, start with T. It's called tetrahedral. Remember this, remember how to spell tetrahedral. Now, tetrahedral arrangement is in a way that it looks something like this. It looks something like this. Now, I'm going to elaborate more later. Silicon dioxide, you need to know it looks something like a tetrahedral arrangement also. Okay? Anyone have any questions? All good to go? Can give me a thumbs up. Next slide. Can go next slide already, right? Okay, thank you, Arisa. All understand, thank you, Hewon. Hey, very nice. Okay, let's moving on. Now, we look at simple molecular structure. Simple molecular structure, because they are very simple, I just now say already, they got weak intermolecular force between each of them. Properties, they are liquid or gas at room temperature. This one you must know. This one you must learn, okay? Simple molecular structure, because they're so simple, I use a little bit of energy, they can break apart already, become liquid or gas. Explanation is over here. Go and read. Weak intermolecular force means that little energy needs to overcome, and hence they are free to move. Now, once again, the explanation is the same. Low melting boiling point. Because of the weak intermolecular force, remember, always come back to this point. Okay? Now, volatile means very easily evaporate because of low boiling point. Why? Why got low boiling point? Because weak intermolecular force require very little energy to break. So you realize, whatever property you use, actually the explanation is exactly the same, right? I tell you, okay, why is it a low melting point? Because why? Weak intermolecular forces between molecules is overcome by small amount of energy. I don't need a lot of energy. I just use slight amount of heat can already, right? Okay, now, simple molecular structure, look at this. They are so simple, they are so small, they are so happy to be with each other already, like that, right? They have weak force with each other, okay? And within itself, they are very happy, right? They are just like to exist as a CO2, like to exist as a water molecule, etc. And that is the reason why when I throw them inside water, they are insoluble. They don't like to make new friends. They don't like to dissolve, right? They just like to stay with each other. They are very happy already, okay? Now, they do not conduct electricity because of the fact that they are covalent. Now, covalent, that means there is no ion, no free moving ion, or no mobile electron. That means they cannot conduct electricity. So far, so clear, Simple molecular structure, your SMS cannot conduct electricity. Don't tell me water can conduct electricity. Don't tell me oxygen gas can conduct electricity. Just think oxygen gas, I put 2 batteries together, can got any spark come across? No have, right? Right. So hence, simple molecular structure cannot conduct electricity. Okay, so far so good. Moving on. I'm trying to speed up a little bit. Now, giant molecular structure, I'm going to touch on diamond and graphite. Okay, silicon dioxide, you go and read yourself. Silicon dioxide is sand. You know, go Sentosa, the beach, the sand, right? Sand. Now, diamond is made from carbon. Now, I explained to you already just now that they form strong covalent bonds with 4 other carbon atoms. Like number 1 is over here. I connect to 1 on top, 2, 3, 4. Each carbon atom connect to 4 other friends. And that is the reason why they are a gigantic network, right? And the keyword is, it is in a tetrahedral arrangement. Okay, that's all finished. Diamond, simple. Graphite. Now, graphite is also carbon. What happened is they are different from diamond. Because they have flat layer of hexagon, what happened is that each carbon atom is bond to 3 other carbon atoms. Now remember, carbon atom look like this. Carbon got 4 electrons. This is the valence, valence shell. Carbon atom got 4 valence electrons. Now, I bond to 1 carbon over here. I bond to 2 carbon over here. I bond to 3 carbon. I bond to 3 friend. Remember graphite, I got 1. Yeah, I draw for you. 1. I bond to 3 friend. Remember, only 3 friend. So I bond to 1 friend, 2 friend, 3 friend. Now, I got 1 electron over here. What happened to this electron? It's just floating around, right? That makes graphite something that is very unusual and very powerful. Each layer of graphite is arranged in this ring, and each ring, each carbon atom is bonded to 3 others. This one I say many, many times already. Now, because of these strong covalent bonds, they are very rigid in the layer, right? In the layer, I cannot tear apart because it's very rigid. However, because there are so many layers, and each layer is held together by weak intermolecular forces, what happens is graphite can easily slide over one another. I apply a force over here, the on top layer will go there. The second layer will go maybe a little bit. The third layer don't even move, right? I push the force on top. This one gonna go there. This one gonna go here, maybe. This one go here only, right? So they can slide over one another. Now, weak attractive forces due to unbonded electron. Now, what is so special about graphite? Okay, we're gonna explore below. Okay, go below your notes. Physical property of giant covalent structure. They are solid at room temperature because it's giant, giant, they strong covalent bond. Each atom is bond to another 3 or 4 atoms. They're solid and they are very hard also, right? Because strong covalent bond. Strong covalent bond means what? Means a lot of energy required to overcome or break the bonds. Now, they have very high melting and boiling point. This one, why? Because you tell me, strong covalent bond law. Strong covalent bond because a lot of energy required to overcome the bonds or break the bonds. Now, once again, because they are so happy to be in this gigantic structure already, they don't like to be in water. They don't like to dissolve. Hence, insoluble in water. Okay, can okay. Now, giant molecular structure have this special characteristic. Just now I say diamond. Okay, carbon got 4 bonds. What about graphite? Graphite, they got carbon, got 3 bonds only. That means that for every carbon, okay, I'll show you again. For every carbon over here, look at this carefully. Where my carbon go? Okay, here. This electron, I put in pink color. This electron, you can see that it is not paired to anything else. It's not bonded, right? And that is the reason why this electron can help graphite to conduct electricity because it's free moving. I'm just there sitting around. If I put electricity through graphite, what happens is that this carbon atom can conduct electricity because it is mobile. Okay? So hence we use graphite in electric motors, in positive and terminal for batteries. Okay, for students who learn electrolysis already or in Sec 4, you're going to learn electrolysis, you will also touch about graphite. Okay, any question? If not, can give me a thumbs up so that I know we can go on. Okay, last part already. Next one is metallic bonding. Thank you, Arisa. Thank you, C. Thank you, Andy. Thank you, YJ. Victoria, Valerie, Sarah, all of you, are you okay? Can Okay, Charlene, thank you. I see your thumbs up. If you're not following, can please let me know so that I can answer your questions if you have any. Okay, Jing En, thank you. I see your thumbs up. Okay, let's move on. Now, last one, metallic bonding. Got 3 types of bonding. Let's recap again. Ionic bonding, covalent bonding, and metallic bonding. Ionic is between metal, non-metal. Covalent is between non-metal, non-metal. Metallic bonding, as the name suggests, metal-metal. Okay? Now, metallic bonding is found in metals. Metal atoms have very few electrons in their outermost shell. For example, like sodium. Sodium got 1 valence electron. Now, what does this mean? It means that this metal atom, they will give up its valence electron to become a positive ion. I'm going to show you a photo. This is how it looks like. So I got a lattice of positive metal ions. And all the electron, all the valence electron is going to just be floating about in the whole metal. Okay, they're just going to flow about in a whole metal. And what does this mean? It means that because they are surrounded by a sea of delocalized electron, they are able to carry a charge. I give it charge, it can carry, it can flow throughout the whole whole structure. All right. Now, metallic bond is known as the attractive force between the positive metal ions. Keyword over here, it is the attractive force between the positive metal ion and the sea of negatively charged delocalized electron. This is the most important thing you need to know. Okay? Metallic bond, positive metal ions, delocalized electron. Basically, whatever that I just tell you in this photo. I got positive metal ion, I got sea of delocalized electron. The attraction is between the positive and the negative. That's it. That is the metallic bond. Now, the structure looks like this. It is a giant metallic lattice. Basically, I got a lot of positive, and I got a lot of electron. Okay. Now, there's very little space between the atoms, and any space will be able to be filled by the electrons. All right. Now, moving on. Okay. Let me just go through this very quickly. You know, metals, they are malleable. Malleable means I can bend, right? Like staple bullet, I can bend the staple bullet. Ductile, I can draw metal into wire. So means I heat metal up to high temperature, I can pull it and make it into a wire. Now, high melting and boiling points, this is because metallic bonds are strong. Remember, positive and negative. Whenever I got positive and negative, they're always very strong because they're opposite charge, they will attract together. Now, good conductor of electricity in both solid and molten state. Now, what does that mean? In solid state, if I piece of staple bullet, it can conduct electricity. Now, in a liquid state or a molten state, they can still conduct because why? The electrons are still there. The electrons still there, they can mobile. They are mobile electrons, they can move about. Okay? Now, they are good conductor of heat. Why? Because they have a lot of mobile electrons. What happens is that these electrons, they're going to bump into each other. When they bump into each other, they will transfer heat energy, right? Okay, and the electrons in one part of the metal will be able to transmit the heat to another part of the metal. Okay, so hence the whole piece of metal become hot. And then they will ask you, why is it that our kettle is made of metal, not plastic? Right? Same reasoning, because metal is a good conductor of heat. And then you will explain it like that, right? Then they ask you, why is plastic not a good material to choose of our kettle? Because plastic will melt, right? Because they are made of simple molecular structure. Okay. All right. Now, structure and bonding. This is a recap. I want you to, for those of you who can just take a picture of this, okay, go back and take this. This is also inside the cheat sheet or the mind map that I'm going to give away later, so not to worry. Okay, now I just want to go to a little bit of practice question. Now, whatever that we have learned in the past 1 hour, maybe 1 hour and 15 minutes, I'm just going to give you some questions, guide you along, and try your best to do this question, okay? Now, I stay here for a little while. What I'm going to do is I'm going to tell you once again. For covalent, what are the two types? They are known as SMS and GMS. Simple molecular structure, giant molecular structure. Then you just see, don't copy. Later I give you the notes, okay? Later I give you the notes. This one don't copy. Listen to me. Now, simple molecular structure, the bonding and the structure is what? Because they are very simple, they like to be happy, they got weak intermolecular force of attraction between simple molecules. Discrete means individual, right? So I got one water molecule, they are joined together with this very weak intermolecular force of attraction. Remember, when got strong only happen when they got positive and negative attraction. Okay, now melting and boiling point is low because why? Weak intermolecular force. They are insoluble, okay, and they cannot conduct electricity. Now, for giant molecular structure, now I'm going to tell you it's a strong covalent bond. Why? Because I'm sharing the electron. I got two atoms. For example, I got H and K. Okay, so maybe not good example. Maybe A and A. Now, A and A is going to share electron. They're going to share by putting it on the table. The table is shared between them. Now, why strong covalent bond? Because I don't want you to take away my electron and run away. I don't want me to give you my electron also. Because why? I want the full octet configuration. I want the full stable configuration. That's why the bond is very strong. They have high melting and boiling point. insoluble in water. They are happy in their gigantic structure, don't like to disturb. You pour water, they also don't care one. Okay. Now, for ionic, got one type. It's called the giant ionic structure. And this happen when they got positive and negative. Okay, positive ion and negative ion, they attract each other. They got strong electrostatic force of attraction, and as follows. This one, most important, they can dissolve in water. Because got positive and negative, water like the positive and negative, they can dissolve the bond. Now, last one, giant metallic lattice. This is for metals. Now, for metals, they got this giant metallic structure. Remember, this one is positive ion and the C of the localized electron. Okay, C of the localized electron. And all the properties are stated over here. Now, I just give you this small recap so that when we do question, we won't be so stunned. Okay, now let's try questions. Okay, now let's look at practice question number 1. W, X, Y, Z. Okay, maybe give you around 1 to 2 minutes. Try and get the answer. Once you're done with the answer, can you please send me in the chat? If you are stuck, okay, remember just now, graphite is what? Giant molecular structure, right? GMS. And graphite, I say already just now, it is the only one with the localized one electron, that one electron that's not paired, so they can conduct electricity. Okay. Okay, he won, I see your answer also. Okay, Andy, I see your new answer. Okay, very good. Right, iodine, I give you a clue. The formula is I2. Okay, silicon oxide and methane. Sarah, I see your answer. Thank you very much. All right. Okay, so I believe most of you are done with the question already. Now, okay, let's see. W 183162. This is a very, very low melting point, right? Very, very low melting point. And they cannot conduct electricity. So W definitely must be what? Simple molecular structure. Simple molecular structure, little energy can already melt and boil. Okay, now X. Let's look at X. Now for X, very high melting and boiling point. And turns out it doesn't conduct electricity. Now that means what? If I got very high melting and boiling point, means I got strong bond. Either strong attraction or strong bond, right? That means if I cannot conduct electricity, definitely it's covalent bond. Because if it's ionic, ion can conduct electricity, right? So in this case, this is a giant molecular structure. Now, why? Y is what? 114, 184, and no. So they are relatively low. That is low. So it may be a simple molecular structure. Okay, and Z. Z is approximately very, very high. And yes, it can conduct. Okay, so in this case, Z either is going to be either a metal. Okay, so it's either a metal or it's going to be graphite, right? Because graphite can conduct electricity. So it turns out that Z is graphite. Okay, Z is graphite. Huh? Now, Y is a simple molecular structure. That means Y can either be methane or iodine. Okay, let's see. Giant molecular structure X. X is what? Sand, right? Sand. Silicon dioxide is giant molecular structure. So definitely this is your answer. And W is methane. Okay, and Y is iodine. Okay, answer is A for apple. Okay, thank you, Marilyn. I saw your answer also. All right. Okay, so this is question number 1. Now, I'm going to now skip over to question 5. Okay. Now let's look at question 5. We are looking at something that is more specific now. Just now we look at the whole chapter in total, but now we look at metals. Now we are saying that the structure of copper is described as a lattice of positive ions in a sea of electrons. Now, which statement are correct? Now, number 1, copper conduct heat because positive ions are free to move. Okay, can anybody tell me, is it true? If true, put T. If F, false, put F. Okay, Clarice, I see your answer. Very good. Okay, Melody, I see your answer also. Very good. I say again, this one, do you agree with me? True or false? Okay, Charlene say true. Okay, she's true. Okay. And you say false. Marilyn say false. Okay, remember, copper is a metal, right? So metal look like this. Metal look like this. Remember, metal look like this, and they got the C of the localized electron. Okay, so whatever this one, the one that I'm drawing in blue is a positive. They are the positive ion. Now, look at this carefully. Positive ion, they are saying is free to move. Actually, are they free to move? No, they are all stuck inside this arrangement. Only the electron can move. The electron can. Okay, so actually this statement is wrong. Okay, copper conduct heat, yes, because of electron, mobile electron. They are free to move. Now, number two, copper conduct electricity because electrons are free to move. True or false? Okay, Andy, I see your answer. Okay, good. Okay, Melody, I see your answer also. Okay, Sarah, I see your answer. Okay, Alina, I see your answer. Okay, Melody, I see your new answer. Okay, good. Okay, Clarice, good. Okay, very good. So yes, this is true, correct. Because electron, I can move, I can give the electron electricity, then electron can move. Okay, now, third one, copper ion are held together because of attraction for each other. True or false? Okay, Marilyn, I see your question. Give me a minute. Okay. Clarice, I see your answer. Andy, I see your answer. Melody, I see your answer also. Okay, Zhishan, I see your answer. Very good. Okay. Halina, I see your answer also. Okay, now this one is a tricky question. Now they are saying copper ions are held together because of their attraction. Now remember, copper is metal. Metal got positive charge. Now, if I got two metal ions that are held together, is it because they are attracted together? I got positive and positive. Will they be attracted? They will repel away, far, far away. I don't want to be with you because why? Far, far away, ma? On like charges. So this is actually wrong. Okay, the lattice is held together by what? Is be copper 2 plus and the electron. Okay, Marilyn, very good. Back to your question. So Marilyn asked a question, very good question. She asked, so the positive ion and the electron, they are different, right? Yes, they are different. Now, let's see here. If I have a sodium atom, okay, sodium atom is what? 2, 8, 8, 1. Okay, pardon the ugly drawing. What my main message to you is this is the only electron that can go away, right? Go into the lattice. So you imagine, if I got many sodium ion, Na plus, Na plus, Na plus, Na plus. Now, this yellow color electron over here, this one over here, what it's going to do is that it's going to delocalize itself inside the structure. That means that the electron can actually move about past all the positive ion. Okay, so the electron actually come from the ion, but they come outside because they can go flow about inside the whole structure. Okay, so the ions and the electron are different. This is a positive ion. Ion means it's sodium. Okay, sodium itself got proton, got electron, but because got more proton than electron, that's why it's positive. This electron is not an ion. Electron is just a charged particle. They are moving about. They come from the atom. Okay, they're just moving about. Okay. All right. Now, and last one, number 4, copper has high melting point due to strong covalent bond. Is that true or false? Very easy question. Okay, Marilyn, I hope I answer your question. Ion cannot move, electron can move. Okay. Okay. Zhishan, I see your answer. Kalina, I see your answer. Okay, very good. Sarah, I see your answer. Marilyn, I see your answer. Very good. Excellent. Okay, Andy, I see your answer also. Okay, very good. Last one. Number 4 is false. Why? Because copper is a metal. Metal engaged in what type of bonding? Metal engaged in metallic bonding. So why got covalent? Covalent only apply for what? Non-metals, right? Covalent, I sharing electron, covalent is for non-metal only. And hence, the only correct answer is D for donkey. Okay? Which statement for copper is correct? Only D. Can any question? Wow, got somebody react laughing face. Okay. All right. Can I? Okay. Nice. Maybe I have time for one more question. Maybe not lah. Okay, I just give it an answer. Now, metals and solution of ionic compound, they conduct electricity differently. This one I just want to drive home the message again. This is a 10-year series question. The reason why I give to you is because I'm telling you that O level, they will always ask this type of question. They will tell you, okay, metal and solution, they are different. Then they ask you, what is the difference? And can you explain the difference? So you must tell me, metals at any temperature, whether it's solid, whether it's liquid, all can conduct. Because why? They have a sea of delocalized electron in the giant metallic lattice structure. These electrons, they act as charge carriers. Keyword is act as charge carriers to conduct electricity. That's it, 1 mark. On the other hand, ionic compound, they are different. Why they are different? Solution of ionic compound, presence of mobile ions inside the solution only. That means I need to dissolve in water. Then my ion will become mobile. If not, it will always be fixed in the lattice. Remember, NaCl, I got this lattice, the square one, Na plus, Cl minus, the cube, the one that look like a cube. So when it dissolves in water, these ions cannot move about, and that's why they can conduct electricity.